Okay, happy Friday, everyone. So let's see, usual announcements. We do have a homework due today. There is a question or two that's related to, I think, power dissipated by resistors. So we're going to cover that today. And then next week, you'll be doing lab number 6. There is a pre-lab, so please complete pre-lab number 6 before the start of your lab section. Lab 6, so you just finished lab 5, which was like the hydraulic version of RC circuits. In lab number 6, you're do RC circuits using electrical components. Okay, and then the other bit of information, it's still like I don't know, a week and a half or a little more away, but quiz number 2 is coming up. That's going to be on March 20th. Couple people were asking me about it already, so I have posted the information on the course website. So let me just show it to you. So share this thing. So here's the course website, and okay, get rid of that. Right. So the second quiz will be during class on March 20th. It'll be a Prairie Learn quiz, 10 multiple choice questions. You'll have 40 minutes to complete the quiz. You don't need to be here in class, just like in quiz 1. You can do it wherever you want, as long as you have a reliable internet connection. It will cover everything up to and including sections 10.1 to 10.3 in the textbook. So although, you might need to know something from prior chapters, the emphasis will be on the stuff that we've covered since the midterm. And so that's going to be chapters 8, 9, and 10. We didn't do all sections of all of those chapters. So I've just highlighted the stuff that we've covered. And then there is a formula sheet that you can print out and have with you when you complete the quiz. The formula sheet is the same style that you've been using for quiz 1 and the midterm. In fact, the formula sheet is basically the same. I just keep adding stuff to it. So for example, parallel and series combinations of capacitors and things like that are out there. Okay, so those are the announcements. And then what I'll do is I'll get this thing back up. Okay, good. So what we spent time on last class was talking about more of a microscopic picture of current in a conductor, and we kind of expressed the current and the current density in terms of like a drift velocity and the number of particles per unit volume, things like that. And what we were able to do is to recover Ohm's law, which for a certain type of material, the voltage across the material is proportional to the current through it, and that constant of proportionality is the resistance. We were able to write the resistance in terms of some property of the material, either the conductivity or the resistivity, and the length of the conductor and its cross-sectional area. So in fact, in lab 4, what you found is that the resistance of a wire was proportional to 1 over its diameter squared. And we can see that here, the area of A is proportional to E squared. And so that's consistent with what you measured in the lab. Okay, so what I want to do today is, where we're headed is in the next, next week, we'll probably focus on analyzing simple circuits. And one of the things that we're going to have to do is when we see a circuit, we're going to do like Kirchhoff voltage loops. We're going to say, if I go around a closed loop in a circuit and I add up all the changes in potential or the changes in voltage, they have to sum to 0. And so you can imagine you could have a circuit with a resistor and a current through it. If I cross that resistor in one direction, I'm going to maybe increase the voltage. If I cross it in the opposite direction, then I must decrease the voltage. And so the question is, when we cross a resistor, should we take the voltage to be positive, the voltage change to be positive or negative? And the answer is it's going to depend on which direction we go, and I want to clarify that right now. I'm going to tell you what the answer is, and then we'll try to confirm that that's the answer. So the rule of thumb is the following. If you cross a resistor in the direction of the current I, the voltage change is negative. Okay, so if you go in the direction of the current, the voltage change will be negative. If you, of course, go the opposite direction, if you cross a resistor in the opposite direction of the current I, the voltage change is positive. Okay, and so those are the rules of thumb, and it's easy to understand why that's the case if we just apply some of the concepts that we've already covered. So let's try that first case. Let's imagine we're going to cross a resistor. Our resistor will just be some kind of, let's say, some piece of cylindrical metal, a chunk of tin or whatever. Okay, and so what we'll do is we'll say, you know, maybe this piece of wire is part of a circuit. I'm not going to draw the rest of the circuit, but it's included in a circuit and there is some current. So we'll say for this first case, the current is going to be going, let's go left to right. And we're going to have potential VA on the left-hand side, and we're going to have potential VB on the right-hand side. Okay, so what do we know? We know that the electric field inside the conductor will point in the same direction as the current, because that electric field exerts forces on the charges in the metal, and that causes the flow of charge, which establishes the current. In a metal, it'll be electrons that carry the current. They'll move in the opposite direction of the electric field, but that corresponds to a current in the same direction of the electric field. Okay, and what do we know about electric fields? We know that they point from a high potential to a low potential. So if we have a current that's going from left to right, there must be an electric field that points left to right. And in order for that electric field to be there, there must be a high potential on the left side and a low potential on the right side. Okay, then let's imagine that we now cross the resistor in the direction of the current I. Okay, and so what we're going to do is we're going to track the changes in voltage. So if we start on the left-hand side, we have voltage VA, and then we cross our resistor, and so that'll be whatever the voltage change across the resistor. So this will be the voltage difference across our resistor. And then once we cross that resistor, we arrive at the right-hand side where we've labeled the potential as being VB. And so then we could just solve for delta VR. So therefore, delta VR is going to be what? VB minus VA. but we said VB was the low potential side and VA was the high potential side. So we're subtracting a large number from a smaller number. And so this is less than 0 or negative. And so that's consistent with our rule of thumb. When we cross our resistor in the direction of the current, we lose some potential. So the voltage across the resistor is negative. We know that the voltage across the resistor will always have a magnitude of I times R. We're just trying to figure out, is the sign positive or negative? And in this case, it would be negative. And so therefore, we would say the voltage across the resistor is minus I times R when we cross the resistor in the direction of the current I. Okay. The argument is the same for the other case. We'll draw it, but you know, it's almost identical. We're just going to now cross the resistor in the direction opposite of the current. Okay, so let's write it out in any case. What we're going to find is that the voltage across the resistor will be plus I times R for the second case. Okay, so case number 2. We're going to cross R anti-parallel to the current I. Okay, so the picture will be similar. So there's going to be our conductor. I'll say this is side VA, this is side with potential VB. We have to, maybe what we'll do is we'll reverse the direction of the current. So if we reverse the direction of the current, that means we have to reverse the direction of the electric field. But electric field points from high to low potential. So this time we've got the high potential on the right-hand side where we've labeled it VB, and then we have the low potential on the left-hand side, which is labeled as VA. Okay, and so what we'll do is we'll cross the resistor in the opposite direction of the current. And so our current is going from right to left. So we're going to cross the resistor from left to right. Okay, and then we just do the same sort of analysis. We say, okay, I'll start on the left-hand side where I know the potential is VA. Then we cross the resistor, and so we'll have this change in voltage across the resistor. And we will, after that, arrive at the right-hand side where we've labeled the potential as VB. And so therefore, the voltage across the resistor is equal to VB minus VA. That's exactly the same as before. What's different is now this VB is the high potential and VA is the low potential. And so we're taking a large number and subtracting from it a small number. And so this is greater than 0 or positive. Just like before, we know the magnitude or the absolute value of the voltage across a resistor is always going to be I times R. We're just figuring out the sign. In this case, the sign has to be positive. So when we cross R in the direction opposite of the current, we get delta VR is equal to plus I times R. Okay, and so this rule of thumb is really important if we want to analyze our circuits consistently and avoid these sign errors. Yeah. Yeah, it doesn't matter. So I guess I'm not talking about a charge, I'm just saying that if we consider the voltage train across a resistor, we could either like do the left voltage minus the right voltage or the right voltage minus the left. That's all I mean. So I'm not talking about like moving charges around. I'm just saying tracking changes in voltage on two sides of a resistor. Yeah. Okay, good. So the other topic I want to do is power dissipated by a resistor. And so you'll need this to finish off one or two questions in the homework. So power dissipated by a resistor. So just to orient ourselves, we are in OpenStax University Physics, Volume 2, Section 9.5. And so that's the last section that we'll do of Chapter 9. So when I was showing you what is quiz number 2 going to cover, it was primarily focused on chapters 8, 9, and 10. So we're going to wrap up chapter 9 today, and then we'll do chapter 10 next week. Okay. So first, let's just remember what power was. So let's recall that power is defined as, so we'll label power P. It's going to be a change in energy divided by a time interval. So you might remember from Physics 111, if you were talking about power, we could have a change in energy. We could calculate that using work. Work was force times, the simplest version of work is force times displacement, and that's a change in energy. So if I take the pen and I drop it, it moves through the gravitational field, there's a gravitational force acting on it. If I take its displacement times the force that's acting on it, that's its change in energy. That's the change in, that's how much kinetic energy it would gain. And then if we want to calculate the power, we would take that change in energy and divide by delta T. So in Physics 111, you would say, okay, force times displacement, so it's F delta X divided by delta T, then you can say delta X divided by delta T was speed or velocity. So in Physics 111, when we're talking about little particles of mass moving around, changing energy, the power, it's usually expressed as force times velocity. So what we're going to do is we're going to see what does power look like for our electrical circuits. In particular, we'll focus on currents in circuits that have batteries and resistors, and we'll start with resistors. So the units of power are going to be the units of energy, which is a joule, divided by time interval units, which is seconds, so it's a joule per second, and that's equal to a watt. So 1 joule per 1 second is 1 watt. Okay, so now we will consider a charge crossing a resistor, okay? Because we're going to track the change in energy of that charge. So let's consider an amount of charge, say delta Q, we'll pick it to be positive, but it doesn't really matter, that crosses a resistor R in time delta T. Okay, and so we could draw that. This will be a similar picture that we've been using already today, but we'll have our voltage A, voltage B here on the side of our resistor. But instead of drawing a cylinder, I'll just use our circuit symbol for resistor. So there's our resistor R, and we'll have a current, let's say I through this resistor, and we'll take a little chunk of charge, delta Q, and we'll have it cross the resistor in that direction. Okay, so just thinking back to what we started with, we said the current will be in the direction of the electric field inside of our resistor, and electric fields point from high potential to low potential. So in this case, our little charge delta Q is going to go from high to low potential. It's going to lose energy when it crosses that resistor. And physically, what's happening is if we have a charge going through our resistor, remember what happens is we have this picture where it scatters off the atoms inside the conductor, or some impurities or some kind of imperfections in the crystal structure of the material. Anyways, it's going through some scatterings. And so that's how it's losing its energy. It comes in with some kinetic energy, scatters around, and that energy gets partially dissipated. Okay, so the charge delta Q loses potential. It loses potential delta VR when it crosses the resistor. And if you remember, we could calculate changes in energy by taking the charge delta Q and multiplying it by the change in potential, or the change in voltage, delta VR in this case. So the corresponding loss of potential energy of the charge is, well, let's see, delta U is equal to the charge delta Q times the change in potential delta VR. And then we said power is the change in energy divided by the change in time. So however long delta T it takes for the charge to cross our resistor. So if the time to cross R is delta T, then the dissipated power is, well, P is going to be delta U divided by delta T, but delta U is delta Q, delta VR, and I could rearrange this. Let's express it, oops, in this way. I'll separate the delta Q divided by delta T and then multiply that fraction by delta VR. Okay. But what is this ratio of delta Q over delta T? We have an amount of charge delta Q crossing some surface in our conductor, and time delta T. What is that? That's the current. So that's exactly what it is. And so therefore, the power dissipated by our resistor is P is equal to I delta VR. Okay, so where does that electrical energy, the energy of our moving charge, if we're dissipating power, like you can't just vanish, where does it go? Yeah, heat, that's exactly right. So if you've ever, you know, the reason why if your phone is working really hard, or if your laptop is doing a lot of calculations, like you're using a lot of the resources, when you touch it, like it gets hotter than if it's just sitting there idle. And that's because it's doing lots of calculations, there's currents flying around, and there's a bunch of resistors in there, and all that electrical energy is being dissipated into heat. So the dissipated energy is transformed into heat. Okay, this also tells us that if we want to sustain a current in a circuit that has a resistor, the resistor will constantly be taking energy out of the system and converting it into this thermal energy, this heat. So you must have something that is always injecting the amount of energy that's lost back into our system. Where's that energy source coming from? From the battery, that's exactly right. So if you want to have a stable circuit operating with stable current, then any energy that is dissipated into heat has to be replenished using some kind of source of energy. And so that could be a battery, for example. Okay, all right. So we know that delta VR is I times R. And so what I could do is I could take this I times R and I can replace it. I could replace the delta VR in this expression. And if I did that, we would say P is I times delta VR, which is I times R. And so that's I squared R. Whoops. Okay, and so here's another expression for the power dissipated by a resistor. And we could do yet another one. There's three variables. There's current, voltage, and resistance. The first expression involves current and voltage, but no resistance. The second expression involves current and resistance, but no voltage. So we must be able to make a third expression that doesn't involve current. So we could say, all right, I know that current is the change in voltage divided by resistance. And I could make that substitution in for I squared. And if we did that, P would be delta VR over R squared times R, which is the change in voltage across the resistor. And then we have R divided by R squared, which turns out to be just 1 over R. And so that's our third way of expressing the power dissipated by a resistor. It's similar to what we had for the energy stored by a capacitor. We could write that in 3 different equivalent ways. And so here it comes up again. Power dissipated by a resistor could be expressed as the current times the voltage, I squared times R, or the square of the voltage divided by R. And so they're all equivalent. They all have to give the same answers, the same results. Okay. So we've already argued that if I want to have a stable operating circuit that involves resistors, and basically all circuits would involve resistance of some kind, even if you don't put a physical resistor in there, whatever connecting wires you use will have some finite resistance. So you're always going to need a battery or some source of energy. So let's calculate how much power a battery supplies to a circuit. Okay, so in a similar way, in a similar way, we can determine the power supplied by a voltage source. such as a battery. We'll see a little closer to the end of the term that there's other sources of voltage besides batteries. And so if you have another source of voltage, you would calculate its power in exactly the same way that we're going to find for the battery. Okay, so what we would have is, here's our battery. And let's say our battery, I'll put a subscript B on there. So delta VB is the voltage difference across the terminals of our battery. And so here's the low potential side. And here's the high potential side. Okay, and we're going to take our delta Q. We'll say it's a positive delta Q, and we'll move it from the negative to the positive terminal of the battery. So it's going to flow through the battery like that. And so our charge, delta Q, which is positive, crosses the battery from the negative to positive terminal and gains potential. Well, let's just say crosses from the negative to positive terminal in time delta t. Okay. So because we're going from the low to high potential side, we've gained some voltage difference of plus delta VB. So delta Q gains potential delta VB and potential energy of delta U is delta Q times delta VB. Okay, so that's the exact same expression that we had for our resistor, except the voltage was the voltage across the resistor rather than the voltage across the battery. So it's the same argument that we've already made. The last step is just to say, well, power is the rate of change in energy. And so if we take our delta U and divide it by our time interval, that gives us the power supplied by the battery. So this is going to be the power supplied by battery. And that's just going to be delta Q divided by delta T times the voltage difference across the battery, which is just I times delta VB. So power supplied by the battery. Okay, good. So what I think we'll do is we'll just do a simple example. And it's a simple example, but it's also a practical one. So let's do an example. Your toaster at home, you plug it into one of these outlets in the wall. The outlet supplies about 120 volts. So that's our voltage source. And then what the toaster has is a long, narrow wire. I remember the resistance, we wrote it down way back at the beginning. The resistance is going to be L over A, proportional to L over A. So if we have a long, narrow wire, if you look inside your toaster, there's this wire that kind of wraps around like a snake kind of pattern. So L is large and it's a skinny wire, A is small. And so that means that ratio of L over A is a big number. And so that means your resistance is big. So they intentionally make the resistance of the wire in your toaster very large. It's also made of nichrome. Nichrome has a high resistivity. So that's another factor of high value of growth. So that's another factor that makes the resistance large. You wouldn't make a toaster with copper wire because it would have a small resistivity and a small resistance. So what we're trying to do is we're trying to make our resistance large so that it dissipates a lot of power. If it dissipates a lot of power, the wire will heat up, and that heat is going to be used to toast your toast. Okay, so example, the nichrome wire in a toaster has a resistance of, let's say, 24 ohms. If the outlet in the wall supplies 120 volts, find, okay, so first find the resulting current. In your toaster, and B, the power dissipated by the resistor, and our resistor is going to be our nichrome wire, and C, the power supplied by the outlet. Okay, so none of these questions are too challenging. How would I find the current? If I know I have 120 volts and 24 ohms, how do I find the current? You know a voltage and a resistance, how do you calculate current? So what do I need? What's in the numerator? Voltage, delta V divided by resistance. And so it's 120 ohms divided by, 120 volts divided by the 24 ohms. Okay, and that turns out to be 5 amps. 100 divided by 20 is, oh, is that right? Yeah, 100 divided by 20 is 5, and then 20 divided by 4 is also 5. Yeah, so that makes sense. Okay, so B, the power dissipated by the resistor. Well, we have a bunch of ways of calculating that. We could do I squared R. I squared is 25, and then times R is 24. So okay, so that is going to be, I think, 600 watts. I think. So I squared is 25 times R, 25 times 24. Yeah, so you've got 100 for every 4, so 24 divided by 6. Yeah, okay, good. So we could also do power is I times delta V, which is going to be 5 times 120. So 5 times 100 is 500, 20 times 5 is 100, so that's 600. So again, that works, that's consistent. And what's the other one? We could do delta V squared divided by R. So 120 squared, I guess, well, whatever. It's going to come out to be 600 watts. So however you do it, you're always going to get the same answer. So this is the dissipated power. The supplied power, power supplied, is just going to be I times the voltage. And we've already done that. And of course, it has to balance. So the outlet is constantly providing energy at the same rate that the nichrome wire is dissipating that energy. And so this is energy conservation. So what happens typically in your toaster is that as this 600 watts of power is being dissipated, the wire gets very hot. So it starts to glow red. Of course, if you look at your coaster, you can always see the elements glowing red. The wire gets heated up to, I looked it up, it gets heated up to around 500 degrees Celsius. So the dissipated power heats the nichrome wire to about 500 degrees Celsius. That hot wire heats the surrounding air, and the surrounding air gets to around 150 degrees. The wire heats the surrounding air to about 150 degrees, which is used to toast the bread. Okay, good. How are we doing time-wise? We have about 10 minutes left. So in the last 10 minutes, what I want to do is I just want to think back to our Kirchhoff voltage loop rule. So remember, the voltage loop rule was a statement of conservation of energy. It just said, just one second. If we take a charge, move it around a circuit, what will happen is it'll experience a bunch of changes in voltage and some corresponding changes in its energy. But if we have a closed loop so that it finishes at the same point that it starts, then all those changes in energy have to add up to zero, or equivalently, the changes in voltage have to sum to zero. That was the Kirchhoff voltage loop rule. Yes.
About what just is it the same principle for any type of heating element like those electrical?
Yeah, like electrical heating is always going to be about this dissipated power. Like in my house, I have like these electric baseboard heaters. It's the exact same. Yeah. Okay, so we're going to kind of shift gears here. So let's recall the Kirchhoff voltage loop rule. Yeah, it would be the same thing in a kettle. You have usually a heating element that's immersed in the water, and you're just dissipating power in that heating element. You could have electrical hot water tanks as well, and it's the same sort of thing. Okay, so the Kirchhoff voltage loop rule said that the sum of the changes in voltage around a closed loop have to be equal to zero. So this is the sum of voltage changes around a closed loop. Okay. And this was really a statement of conservation of energy. All right. So what we want to do now is Kirchhoff has a second rule, and it's called the Kirchhoff junction rule. So what I want to imagine is that we've got a wire, and it's going to carry some current, I. And then it's going to come to a junction. So somewhere where the wire breaks into, it's like a fork in the road, right? Where you can choose to take different paths. And so maybe here's a junction where there's 3 different paths that the current could follow. And so there's going to be a path 1, and a path 2, and a path 3. So if we imagine what current is like a collection of charges, and they're all flowing kind of together, and they're going to come to a junction, and all these individual charges, they're going to have to take one of the 3 paths. Individual charge, like an individual electron, is not going to break up and like partially take path 1 and partially take path 2, an electron takes one of the 3 available paths. And so some of the charges in the original current will take path 1, some will take path 2, and some will take path 3. There can be no charge lost or created at the junction. So whatever charge comes into the junction must leave the junction. So when a current encounters a junction, some takes path 1, some takes path 2, and some, in this example, there's 3 paths, takes path 3. However, the net current into the junction must equal the net current leaving the junction. So there can be no charge created or destroyed at the junction. And so, whereas the voltage loop rule was a statement of conservation of energy, this junction rule is a statement of conservation of charge. So conservation of charge. And so the junction rule really can be stated very succinctly in the following way. So current in equals current out. So in our example, we had current I coming into the junction, and then we had 1, 2, and 3 heading out of the junction. And so in our example, we would say I is equal to I1 plus I2 plus I3. We could do one other trivial example. We could have a more complicated, well, I mean, it's hard to get more complicated. You know, I could add another branch or something, and I could say, here's I1, here's I2. I'll just pick some random directions here. I4, and let's say this is I5. And so if I want to apply the junction rule, all I have to do is find current into the junction. And so I1 is headed towards the node or the junction. I3 is headed towards the junction, and so is I4. But I2 is away from that node. I5 is away from that node. And so the junction rule requires the current in, which in this example includes I1, I3, and I4. So this is current in, must equal the current out. And in this example, it's I2 and I5. So this is current out. And it'll turn out, as we'll see next week, that carefully applying the Kirchhoff loop rule and the Kirchhoff junction rule is really the fundamental things that we need to analyze simple circuits. And so we'll do some simple circuits involving batteries and resistors next week, and we'll analyze them using the 2 Kirchhoff rules, the loop rule and the junction rule. Okay, good. Thank you very much. Have a good weekend.